welcome in this tutorial video. We are going to see how to perform a frequency analysis with EEGpal. The idea is to study the brain waves, which could be used as biomarkers or to study the sleep states. There is 5 important frequency bands. There is the gamma, the beta, alpha, theta, and delta. In this column, you have the frequency range for each of those bands. The frequency analysis consists to study the power of those frequencies. In other words, it tells you how much this frequency contributes to the EEG signal in the time domain. We will work on the epoch file generated during the epoching step. I remind you that we activate the option Merge Epochs into one file. It means that it records all the accepted epoch into a single file. It permits to keep all the clean signal from our EEG recording. Now let's import those files. You will find it inside of the output folder of the epoching in the epochs subfolder. Now let's open the frequency module. The windows is organized into 5 panels. In first, you can choose which method you want to apply to study your frequency. The fast Fourier transform, or FFT, permits to transform the signal from time domain to the frequency domain. It uses a standard function from MATLAB, which is well established. The FFTA is a variation of the previous method. The problem with the classical FFT is that you lose the polarity information, which is needed to compute the inverse solution. The FFTA is a method proposed by Denis Brunet and implemented into CARTOOL to restore those info. Please consult the FAQ of the user manual for more detail. And the third option do the same job as the classical FFT but used the function developed in EEGlab. It provides similar results as the FFT but with a different scale. Again, please refer to the FAQ from the module manual to have more detail. Let's see the analysis parameter. In first, you can specify which period of your file you want to study. By default, it will consider the whole file, but you can change the onset or the offset. To note that the value of offset and duration is relative to the first input file. However, the other input file could have a different length, and those values will be adapted for each of them. The window size is important. You are going to cut your EEG file into sub-windows. EEGpal will automatically study the frequency power in each of those windows to give the evolution of frequency power through time. So you can specify the window size here. Usually, this value corresponds to the sub-epoch duration you specified in the epoching model. This parameter allows you to specify if you want that windows have an overlap period. For example, if you have windows with a length of 100 time frame, if you specify an overlap of 20 time frame, it means that the next windows will start at the position 80 of the previous one. This is mainly used to artificially increase the temporal resolution in case of short recording. Depending of those parameters, it will tell you how many windows will be studied. Again, the value here is valid for the first input file and will be recomputed for each file because it depends of their length. The frequency resolution defines the steps which will be studied. For example, here, EEGpal will study the power for the frequency 0, 0.5, 1, 152 until 512 Hz. This resolution depends on the window size. For example, if I change my window size for 100, you see that now the frequency step will be of 1 Hz. The range parameter will permit you to limit the frequency range which will be studied. In our case, we will study the frequency between 0 to 30 Hz. The next option permits to specify if you want to sum the steps results into bands. It is usually what you want. Here, I would like to study the alpha and beta bands. So I will specify as input 8 to 12 for alpha. I put dots, comma as separator, and I specify 13 to 30 for beta band. Next is the windowsing function. The drawback to study windows is that it creates unwanted effects associated with discontinuities at edge. Indeed, the Fourier transform need to work on continuous signal, and to overcome this problem, he will consider the signal as periodic. So it makes problem when the start and the end of the segment don't match, as in this example. It creates a discontinuities introducing high frequency that is not present in the original signal. It has for consequence to make a dispersion of the energy. As you see in these pictures, you have a signal of 13 Hz. The signal in black study when you consider a continuous signal, and you see that all the power in the power spectrum graph is located at 13 Hz. Then if you windows this signal, as in blue or in red, you see that in the power spectrum, the 13 Hz power will be dispatched into neighboring frequency, which make the peak less clear. To overcome this problem, we can use windowsing function, which will modulate the signal amplitude at the border. So you have the choice between anning, which is particularly suitable to isolate narrow frequency band like alpha and beta in EEG, or the amming, which attenuates less the edge, which reduce the loss of information at edge, which is more preferable when you are interested by wider frequency band. The most popular in EEG will be the anning. Do note that if you are in EEG mode, you don't have the choice and it will automatically apply the anning algorithm. Next is the normalization. There is two cases where the normalization is advised. The first one is when you want to compare two different populations, like patient or control. Indeed, there is inter-individual power difference which take origin from the physiology, the thickness of the bones and the scalp, and other factors. It makes the comparison between individuals difficult. So the best solution in this case is to divide the power of each frequency band by the average power in the frequency range of interest. It is what the option by global average power offer. Practically, it will average the power inside of the frequency range you specify. It's why it's important to limit this range to your frequency of interest. You see in this example that the output will reflect now how much the power of alpha and beta will be in comparison to the average. You see in this graphic that power inside of alpha band is lower than the average power, because it's below 1, and for the beta the value is bigger than 1, mean that the power is more important than the average power. The second case is when you want to compare the power between bands. Naturally, the power of low frequency are higher than high frequencies. It makes the comparison between bands difficult. In order to overcome this problem, we can flat the power by dividing each frequency band by its average power. It is the option offered by mean per frequency 1 over f correction. In last, EEGpal offer also the option to normalize by the log transfer. This is a method frequently used in literature because it's the default option of EEG Lab. However, recent publication has pointed that it could introduce problem, and it's why it's not recommended anymore. The reference of this publication is in the description of this video. Here, you have the possibility to downsample your data if you want so. Now the saving option. There is two sections. The whole range power spectra will save the power for each bin in the frequency range that you have specified here. So for example, you will have a value for 0, 1, 2, 3 until 30 Hz. the frequency band section will allow you to save the power for each frequency band that you have specified here. In column, you have the possibility to save the power spectrum density or PSD, which will save the frequency power for each electrodes inside of each window. It is used when you are interested to study the distribution of frequency over the scale. The second option is the global power spectrum or GPS, which average the frequency power over all electrodes. So you will get one value for each windows which reflect the global frequency power over the scale. Finally, for each case, you can save either the average results over the time windows or to save the power for each window separately to study the temporal evolution. Let's finish by the output option. By default, the PSD are recorded in the FREC file format, which can be opened by CARTOOL. It allows to visualize the results as well as doing simple statistics. However, if you don't work with it, you can save the output into mat file for MATLAB. The dimension of the output array will depend on the option. For example, in the case where you study the whole spectra with a separate value for each time windows, you will have a matrix of 3 dimensions with the number of frequency bin, the number of electrodes, and the number of windows. If you work on the frequency band separate per time windows, it's also a 3-dimension matrix, but in this case will be the number of bands by the number of electrodes by the number of windows. In both average case, it will just replace the last dimension by the mean. For the GPS, you have the possibility to record the results in Excel file, CSV file, or in EP if you want to open the output in CARTOOL. Then you have the classical selection of the output folder and a suffix string for the file. And then we run. In my output folder, I got one folder for each participant. And for each file, I got my outputs, so the FREC for the PSD as well as the Excel for the GSD. So if I look at the spectra results, CARTOOL is displaying me the power spectrum for every electrodes and every frequency bin. If I'm interested by the power spectrum in my frequency band, CARTOOL gives me the power spectrum for each electrodes and each windows here for the alpha and here for the beta band. Now, if I want to look to the GPS, especially the case of the spectra, I got a matrix with each column, which is a frequency bin, and in line the time windows. And if I'm look to the band, see a file with one column for the alpha, one for the beta, and the detail for each time windows. It concludes this video about the frequency analysis in EEGpal.